A warm welcome to all the viewers. In this session, I will be telling you the difference between one sample z-test and a one sample t-test and how to solve them manually. This session is going to be quite important, covering all the details pertinent to both of these tests and is especially useful for the beginner researchers. So stay tuned, keep watching. Now, as we know, we usually conduct a t-test or a z-test to compare the sample means with the population mean. And to compare the sample mean with the population mean, we frame certain hypotheses. For an instance, we frame a hypothesis that is, there is a significant difference between the sample mean and the population mean, which becomes our alternate hypothesis. And there's the opposite, which is known as null hypothesis, which states that there is no significant difference between the sample mean and the population mean. So we are going to test these two and arrive at a decision on whether we can reject the null hypothesis and go with the alternate, or we are unable to reject the null hypothesis. So this is the essence of both of these tests. They are used to compare the means. Now, what is this significance level? As I have told you in my previous video also, you might like to go back and check on the previous playlists to know more about the empirical rule of normal distribution and also to know about confidence interval, significance level, z-score, z-statistic, and t-statistic. Significance level is the predetermined probability of committing a type 1 error. Now, what is a type 1 error? It is rejecting a true null hypothesis. So when in fact you shouldn't be rejecting a null hypothesis, you mistakenly reject it. This is known as type 1 error. So if we reduce the probability of committing a type 1 error, then we save ourselves from incorrectly rejecting a true null hypothesis. Right? So that is why we usually keep a significance level of 0.05, which is a 5% chance of making a type 1 error. While a p-value is the probability of an observed result occurring by chance if the null hypothesis is true. So, if the p-value is less than 0.05, that is the significance level which we set. In that case, we reject the null hypothesis and go with the alternate statement. So, p stands for probability of an observed result occurring by chance if the null hypothesis is true. So, by setting the significance level, you reduce the risk of rejecting a true null hypothesis. And when you don't reject a true null hypothesis, then what is the chance that you are getting the probability of that observed result? The decision is made by you on a chance level. So that is p-value. Now let us take one example and try to solve it manually. First, we will go for one sample z-test. In this, a light bulb factory claims its bulbs have an average lifespan of 1000 hours with a known population standard deviation of 100 hours. Now you might recall that in a z-test, the population standard deviation is known to us and the sample size is greater than 30. A quality control manager tests a random sample of 50 bulbs and finds a sample average lifespan of 1050 hours. Is this difference statistically significant at a 0.05 significance level? And this significance level alpha, which we have recently spoken about, is set at 0.05. So this is a table which shows us hypothesis testing critical values. Now, what do you think? In this case, is it a left tail test, a right tail test, or a two tail test? Again, I have described all these terms in my previous video on important statistical terms, hypothesis testing, wherein you can check it out. What are these three types of hypothesis testing? In this case, we are just saying that we want to find out whether this difference in the lifespan of this sample of 50 bulbs is different from the population working hours or not. Because in sample, it is 1050 hours, which is more than 1000 hours, which was for the population. So that means it's a two-tailed test. Understand one thing more. Critical values for the z-test are fixed and depend only on the significance level and number of tails, not the sample size or degrees of freedom as in case of a t-test. So in case of a t-test, you have to assess the degrees of freedom, which is subtracting 1 from the sample size. You get the degrees of freedom to get the critical t value from the t table. But in z-test, you don't require these because they are fixed and only depend on the significance level and number of tails, not the sample size or degrees of freedom. The formula for executing a z-test, wherein x bar is the sample mean, mu is the population mean, sigma is the standard deviation divided by under root of sample size. So when we come to the steps, the null hypothesis is the true average lifespan is 1000 hours. That means there is no difference between the sample mean and the population mean. It is the same. The alternate hypothesis is the true average lifespan is different from 1000 hours. That means sample mean is different from population mean. Now, to calculate this one which you see, sigma divided by under root of sample size is also known as standard error of the mean. So you can compute it by putting the standard deviation value of 100. You see here standard deviation of 100 hours divided by the under root of sample size, that is 50 bulbs. You get 14.14 hours. Now, next step is calculating the z statistic using this formula. You just plug in the values. Sample mean 1050, population mean 1000, and standard error of mean which we have calculated as 14.14. We arrive at a figure of 3.54. Now the next step is determining the critical value and make a decision. So for a two-tailed test, you just look at this table. For a two-tailed test at alpha, which is the significance level of 0.05, which is specified in the question, the value is plus minus 1.96. So this is found using a standard normal distribution table. That means on each side of a normally distributed curve, you have 2.5% scope of getting the extreme values. And within that, the area covered under the body of the curve is 95%. But since it's a two-tailed test conducted at alpha 0.05, we need to check in the values of critical z-scores in the table, wherein the area covered under the curve is 97.5%, because we don't know the direction, whether it is on the right side or on the left side. It can be just on one side, right? It cannot be on both of the sides. So when you look at that table, you'll find out that this value is 1.96. Area under the curve is 97.5%, alpha 0.05, and that's how you get plus minus 1.96. Now, if this calculated value does not come within this range of minus 1.96 to plus 1.96. It is outside this range, which is true in this case. You see, it is 3.54, which is greater than the positive critical value of 1.96. So it falls into the rejection region and we reject the null hypothesis. So by rejecting null hypothesis, we mean, you see the null hypothesis? The true average lifespan is 1000 hours. So the sample mean and the population mean is the same. There's no difference. So when we reject it, we say the true average lifespan is different from 1000 hours. So the sample mean lifespan of 1050 hours is statistically and significantly different from the factory's claim of 1000 hours. So I hope now it's very simple to understand and easy for you to remember that how to conduct a one sample z test, what does it help us to know, and how to calculate it manually using this formula. Now let us go to one sample t-test. The example given over here is average time taken by the population of senior secondary students for a 100-meter sprint is 8 seconds. A researcher wants to test the effectiveness of a new training method. He conducts a study with a small sample of randomly selected 25 students and records their 100-meter sprint timing, which computes to an average of 6 seconds and standard deviation of 2 seconds. Now you know in one sample t-test, the sample size should be less than 30 and the standard deviation of the population is unknown. So the population standard deviation is unknown. That's why we go in for one sample t-test. If it's known, we go in for one sample z-test and the sample size should be greater than 30. Does the new training method significantly reduce the sprint timing? Now you say, what type of hypothesis testing is this out of these three? Left-tailed, right-tailed, or two-tailed? When there's an inverse relationship, as I discussed in the previous video also, it is known as left-tailed hypothesis. So in this case, we have a left-tailed hypothesis because the new training method significantly reduces the sprint time. We are going to check that. Accordingly, we will build our hypothesis. So the null hypothesis is the new training method does not reduce the sprint timing and it is still 8 seconds or maybe more than 8 seconds, right? It is still 8 seconds or more than 8 seconds. The alternative is the new training method significantly reduces the sprint timing, meaning the average time is less than 8 seconds. So that is how you represent it. This is a one-tail test because the researcher is only interested in whether the time is reduced. Okay. So select the test and significance level. Sample size is small. I've already told you standard deviation of the population is unknown. So we go in for one sample t-test. You use this formula. You plug in the values into this formula. This is the sample mean. This is the population mean. This is the standard deviation of the sample. If you recall, in case of one sample t-test, this is the standard deviation of the population. Here we have the standard deviation of the sample. Putting these values, you get minus 5. You see here, minus 5. 6 minus 8. 6 was the sample mean. 8 was the population mean. 2 is the standard deviation. You see 2 seconds. And divided by under root of sample size, which is 25. You get minus 5. Now we have to compare this with the t-value, the critical t-value for a one-tailed test with alpha of 0.05 and degrees of freedom, which is n minus 1, 24. So when we look at a t-table, in a t-table, let me show you how it looks like. You see student t-distribution probabilities table. For a one-tailed test, at a significance level of 0.05, this is how you check it. One-tailed test, significance level of 0.05 and 24 degrees of freedom, right? So this is 24. The value is 1.711. You see here, 1.711. So we have to Compare the calculated value with this stable value of 1.711. In case that calculated value is outside the range of minus 1.711, in that case, we call it that we can reject the null hypothesis and go with the alternate hypothesis. And now you see the value which we got is minus 5 after the calculation. It is less than the critical value minus 1.711, meaning it falls within the rejection region. Therefore, the null hypothesis is rejected and the data provides sufficient evidence to conclude at the 0.05 significance level that the new training method significantly reduced the spring timing, as mentioned in our alternate hypothesis also. So this was all about how to manually do one sample z-test and one sample t-test. I have explained to you in a very simple and easy to understand language so that you can remember it forever. Stay tuned, keep watching. Thanks a lot.